Okay, this is the first video from chapter 24, and really it's at this point that we start getting at stuff that is not review. Last year you learned how to calculate the electric field for point charges. And I showed you a horrible calculus-heavy method for calculating the electric field of continuous charge distributions, which, by the way, will work for any charge distribution if you are sufficiently clever to actually evaluate the integral. But there is a much simpler way of calculating the field of continuous charge distributions if they happen to have a high degree of symmetry. And that is something called Gauss's law. But before we can understand Gauss's law, we need an additional concept called electric flux. And last year, you heard about something called magnetic flux, which was the number of magnetic field lines that went through a loop. Electric flux is very similar. It's the number of electric field lines that pass through a surface. So if you've got a surface oriented like that, say it has area A, and there are field lines that go through it, and let's say if those field lines are perpendicular to the loop, or if the field lines are perpendicular to the surface, then the flux, phi, and we'll put a subscript E to indicate that we're talking about electric flux rather than magnetic flux, is equal to the magnitude of the field times the area. But let's say now that the electric field is not parallel to the surface. What we'll do is we'll define the normal line that is perpendicular to the surface, and we'll define an angle theta the electric field makes with the normal line. So theta is the angle between the electric field and the normal. And we notice that as theta increases, as the electric field points more and more parallel to the plane, the number of field lines that actually go through the surface decreases. Until, if the field is parallel to the surface, none of the field lines actually go through the surface. And so that tells us that the electric flux is equal to E times A times the cosine of that angle theta. When theta equals 90 degrees, cosine is 0, and the flux is 0. When theta is 0, that means the field is perpendicular to the surface, and the cosine is equal to 1. And we've seen this before. We have something times something else times the cosine of an angle. That's a dot product. And so if we define the area vector as having a direction that is perpendicular to the surface and a magnitude that is equal to the area, we get phi E equals E dot A, where the area vector points along the normal. Either one of these equations you should memorize. Pick one, whichever one you like more. If you like vectors, and I hope you do, think about the dot product. If you don't like vectors, you can use this equation. Now let's say, most of the time when we're using Gauss's law, we're going to be using closed surfaces, meaning they enclose an area of space. Also, most of the time, those surfaces are going to be curved, not flat. So let's say we have some amorphously shaped three-dimensional closed surface. And it has field lines that go in, come out, go in, come out, at different spots. What we'll do is we'll break the surface up into many small, almost flat areas, dA. So that is dA right there. And dA can be written as a vector, which is where the area vector dA points perpendicularly outward, and that angle is theta. And so The flux we can write as the sum of all the E dot dAs, and since the dAs are very, very tiny and there's many, many, many of them, we write the integral for the flux that way. Now these integrals can get horrible quickly, but most of the time when we apply Gauss's law, it will be possible to write the flux as E times the integral of dA. So E will be constant over the whole area of the surface. So it comes out of the integral. Well, the integral of dA, that's just the total area of the surface. And that's quite simple. Another thing to point out, if you have a closed surface, we will conventionally say that dA, the area vectors, point outward. The result of this is that when you have field lines that point into a surface, so this one, and this one, produce negative flux, and field lines out of the surface have positive flux. So if a field line comes out of the surface, that makes positive flux. Field lines that go into the surface make negative flux. And an example, this is part A of problem 3. You should do the other parts of problem 3 for tomorrow. What you've got is a cube, x, y, and z axes, and we have an electric field equal to 6 newtons per coulomb in the I direction. So it points like that. We want to find the electric flux through the right face of the cube given that electric field. Now there's two ways of going about this. First way, we could find the area vector, which points in the y direction. And if we say that the flux is equal to E dot A, or EA cosine theta, the angle between the area vector and the electric field is 90 degrees. And so that means the flux through that side of the cube equals 0. And that was easy. Another way of thinking about it, the electric field is like that. You have some field lines that are on one side, that are on the right side of the surface, and they stay on the right side of the surface. Other field lines are on the left side of the surface, and they stay on the left side of the surface. No field lines actually go through that side of the cube, so the flux through that face is going to be 0. Tomorrow I'll be checking the rest of that problem, as well as question number 2.